In this part of Unit 1, we will talk about asymptotics and the most famous version of it, the big O notation, which goes hand in hand with our machine models, which were also, as you recall, changing with the input size. The machine grew together with the problems it has to tackle. And it often also is necessary to do a meaningful analysis to go to asymptotics. So we'll see what that means today. Asymptotics basically means approximate something around infinity. So this is the intuitive part to keep in mind. Whenever we say asymptotics, this is what I mean in that sense. It's approximate something for big inputs, because those are the ones that interest us. It's often possible for small special cases to do better, and you can do that, but that's usually much easier. Getting the big problems, the limit for large inputs right, that's the challenge. So we look at large inputs, or somewhere down the road on the horizon. It forces us to abstract from some details, and that's usually a good thing. You might have heard this quote, premature optimization is the root of all evil, which is a well-known quote among programmers that you can spend hours of your time optimizing every little bit of your code, and then you notice it's actually not the part that runs often, and all your effort was wasted. You polished a certain part, and no one's ever really using that code heavily. An asymptotic analysis can pinpoint you to the parts of the code that are executed very often and which are relevant, so that you can focus your optimization efforts on these parts. It's also good that it simplifies the analysis. If we want to predict how fast an algorithm is, it's often necessary to abstract a bit, and asymptotics is one way of abstracting from what happens on small inputs. So here's a concrete example in a more technical sense what asymptotics means for us. We have a function that could be the running time of an algorithm when it's given the worst input for size n. So we measure the size of the input, and then we take the pessimistic point of view. It's the worst input that we see. And then f of n could be the running time of some algorithm. And let's suppose we were really, really good at this, and we were able to exactly determine how long this algorithm takes. And it might be a nice function like this, a closed form, which is already the best thing you usually can get. And you can plot the function. You see that there's these little small jumps, etc., coming from the ceilings, floors. So this might be what you get out of your analysis in the good case. But it's very hard from this function to really get a grasp on how fast that is. It's just overwhelming. The term is too big. And what asymptotics can do for you is, so you replace this long, complicated expression with this much smaller, short expression. And if you're not too unlucky, the two functions are plotted here, and they're very, very close. So you get a very accurate approximation if you take an asymptotic approximation for this function. It's not always quite as easy as in this case. You might notice that all I had to do was drop the other summands from this term. That's something that often happens, doesn't always happen. That's why we will talk about the mathematics behind this. But the goal is to represent a function that's complicated by something that's simple, and allow a certain error in that, but hopefully not a big one. Now here's the actual math behind this. I guess it looks a little scary at first, but let's go through it step by step. These are three different notions, and the simplest is this tilde notation. F is tilde G. That's the one that I used here on that slide. That's an instance. That's the most precise one. That's the most desirable one, but sometimes it's hard to get, so we'll also use the other ones. Two functions are in this tilde relation, or we say they're asymptotically equivalent. If you take the quotient of the two, and that quotient converges to 1. Fine? So they're in a relative error sense speaking, you can replace one function by the other, and the relative error you make goes to 0. That's a fairly easy criterion to check, but sometimes it's hard to guess this right leading constant. That's why there's the other notation, the big O notation around, which is much more widely used, and it's a little more flexible. And in that case, we also take the quotient of the two functions, but we only want it to be bounded. It can be 5, it can be 0, it can be 5,000, or it can be a number between 5 and 10, and it changes all the time. All that is fine. Bounded just means strictly less than infinite. There's some upper bound for these quotients. Whenever two functions satisfy this, then we say f of n is in big O of g of n. There's another way to express this using the limit superior, if that helps you. If not, essentially ignore it. What George will tell you in the tutorials on a couple more examples is, if you just take the quotient of those two functions that you want to check, if one is bigger than the other, then usually computing this limit, like here, will tell you some result. It will be some fixed number in most cases, and then the answer follows from that already. There's variants of big O that express essentially the opposite. There's big omega, which says that the other relation holds. So omega means that you take the quotient in the other direction, and that is bounded. Or you could also say it doesn't go to 0. So it's maybe the time to show this more intuitive picture for those big O classes. What you can't see from the definition I just showed you is that big O is an upper bound. It's always something that expresses an at most relation. If f is in big O of g of n, then f is at most g of n. But that statement is not exactly true. It's constrained to be, you can add a constant factor to g, and that's fine. And it might be necessary to discard a few small input sizes. So in the picture, it means g of n might be small, but there's a constant c. It could be 100. So that if I multiply g with that constant, I'm bigger than f. And it could also mean that this statement is only true for large enough n. It might be false for small n. And that's fine. So big O means an upper bound. F is at most g of n. But that's only true up to constant factors and for sufficiently large n. In the same sense, big omega means f is at least g of n, again up to constant factors and for sufficiently large n only. The third in this row is big theta, which is just expressing both. So for f to be big theta of g, it has to be big O of g and big omega of g, which means f and g are of the same order of growth. They're the same. They're Well, they are the same up to constant factors and for sufficiently large n if you take the same here, the same constraints. That's a bit, I'll come back to that statement. You have to be a little careful. But okay, it's on the slide here anyways. So for you to keep in mind, big O is an upper bound, big omega is a lower bound, and big theta is essentially the same growth. And the precise details to check is take the limit of the quotient. There's two more of these notations that are not quite as used as much, but they're still sometimes useful. They're the strict versions of the capital letter counterparts. So little o is the same as big O, except that it doesn't allow equal in the asymptotic sense. So what it means is if you take the quotient f divided by g, then this has to go to 0. That's stricter than requiring it to just be bounded. Here it was fine if it goes to 1. So if f is tilde g, that also means f is big O of g. But for the little o of g, that's not allowed. Then f has to be strictly smaller, has to grow strictly slower than g. And big omega, little omega, sorry. Little omega is, again, the counterpart to big omega, so it's a strict lower bound. Okay? We will mostly use the capital ones, big O and big theta, and occasionally the tilde if it's possible to show something stronger. If you look at those pictures, you might be tempted to say, well, let's forget about this complicated mathematical definition with limes, superior, and all that. Why don't we just plot the functions and then we see which one is bigger? And that's most of the time fine. However, there are nasty functions out there. The space of mathematical functions that these definitions should apply to is very vast, and there's a few bad villains among those. This is not what you will usually have to deal with, but I want to show you an explicit example of bad functions that can make you fall into this trap. Here's here are two functions, and they're plotted 3 times. It's a bit small, but maybe you can see that the only thing I changed from the first to second and third plot is the limit of the range. So here the first one goes from 0 to 2,000, the second from 0 to 10,000, and the third from 0 to 200,000. On the first one, it looks like, okay, green is bigger initially, but then red catches up. So maybe red grows faster in the limit. And that seems to be true up to 10,000, so red is taking off. But then when you come to 200,000, it has completely shifted, and now green is much bigger. Those must be fairly weird functions, right? The problem is, if you only see one of those plots, especially either this one or just this one, you might well be tempted to say, I know what's going on, so I don't have to look at limites, and quotients. I can clearly see from the picture what's going on. But it turns out that those two functions are actually asymptotically equivalent. They have the same growth, and they even have the same constant in front of them. The nasty part here is, okay, I made this example up to fool an attempt to see in the plot what's going on. So those are nasty functions that don't usually occur in examples. But if you want to check out this post, there's also examples that actually occurred in research where people tried to guess the order of growth, and it was wrong because the plots looked very similar. In this specific example, you can debunk those two functions as exactly being the same asymptotically if you draw a log-log plot. So this has a logarithmic axis on both x and y, which essentially means you get much more range compressed into this plot. And then you see that the two functions are essentially just a little wiggling around each other. But you can create another example so that you would have to go even further, and even on the log-log plot, it would look like before. So there's no clean way to just go by pictures. You never know when you have plotted far enough. That's why I torture you with all those limit computations. That said, most of the time the picture will do fine. So I encourage you to take pictures to get a first impression. But don't be fooled into believing that this is a proof. Okay, let's do a quick check of your understanding of the basics. I put in 1 minute. Is everybody done anyways? Okay, we'll leave the countdown just to make it a little more dramatic. Okay, most of you voted for G is theta of n in that case, and that's true. It was on the slides, wasn't it? But just to double check again, so f in big O of G means f is at most G of n, blah, 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 up to constant factors and up to being only true for large enough n. But if f is at most G, then G should be at least f, and that's exactly what this expresses. Now there's a little catch in that the way I showed you the definitions, and there's a small problem. Again, won't usually occur in the applications we have, but I want to point it out in case you're wondering what happens. What if a function is actually 0? A function could be just always 0, in which case dividing by it is a really bad idea. If f is just 0 at a certain amount of, well, up to a certain maximum n, we could be fine with that. We could just cut out the so-and-so, the first so-and-so input sizes. But if it's 0 an infinite number of times, then these definitions that I presented you just don't really make sense. So we will usually assume that our functions are not always 0 or not infinitely often 0. So in some sense, the last answer is correct too. If you thought about this nitpick, well done. If not, also well done, because we won't deal with it most of the time. Here are some more examples. You've already seen one example of the tilde type, so here's another one of this somewhat more complicated function, and it was possible to get the first order approximation, so this asymptotic equivalence, by just dropping those smaller summands. And you can further abstract the constant 20 here and say it's big theta of n cubed. Now, how would you actually prove this? What you would have to do is take the limit of the function and whatever's in the theta, or you might include the 20, and you would have to compute the limit of this. Now in that case, you might know that there's a special rule, or in this case, you can simply divide everything. So you divide each summand separately by this, and then you just know that there's a 1 left plus the limit of, you can cancel that, so it's n log n divided 10 n cubed. So you could write it like this and further conclude that those go to 0. And then you would have computed this limit. I'm fast forwarding here a little bit. So I'm splitting up the fraction, and then you would have to know that these go to 0, which would be another proof. But on the other hand, this module is not about calculus or analysis. So I don't really want to go in a lot of detail about how to compute limits. We will use this as a tool, but it's not the main idea of this module to teach you limits. So I want to suggest another tool for you that is not available in the exam, but then again, I won't make you compute very complicated limits in the exam. Basic ones like this first one you should be able to do. More complicated ones, again, do a calculus course if you're interested in those. Well, quick hands, who has used Wolfram Alpha before? The rest has never used it? Or you didn't show? Well, either way, I mean, it's a very useful website. If you've never seen it before, definitely spend some half an hour and play with the examples that they provide down here. You can just type in math in a fairly natural way. You can, for example, say limit of this function divided by this function as n goes to infinity. And for most functions where I'm able to compute it, Wolfram Alpha is able to compute it as well. That's another reason why I like the definition of big O, etc., that I presented with taking limits. There's another one that you will see in other books or might have seen in other modules before where it starts with there exists an n0, so that for all n bigger than n0, blah, 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 some inequality holds. Those kind of statements are tough to prove with computer algebra, but limits is something computer algebra is very good at. So we could say this was by Wolfram Alpha, so we believe it's true. Let's try another one. In this case, you might know that there's a rule for simplifying logarithms. A power inside the log goes out as a factor, so that's same as 6 log n. And then the double log grows smaller than the single log. So once you divide both sides by log n, the second term will again go to 0, and the first one will go to 6, so that's bounded. And the cheating version is you type it in. And okay, here's the glitch with logarithms. I'll come back to this, but first, the limit is some number, and the number is not infinity, so it's bounded, right? That was enough for proving big O. Now for proving the big omega, which we also need for theta, it's actually enough that this number is not 0. If it's not 0 and not infinity, but some actual real number in between, then it's a big theta. That's a proof for big theta. Okay? So there's two ways how you can prove that something is in big theta of something else. You can separately prove big O and big omega, or you can show that the limit is a number between 0, strictly between 0 and infinity. So it's not 0, it's not infinity, it's something in between. Then you're in big theta as well. Now, I wanted to say something about logarithms. You will note that I used LG on the left. And by that, I always mean log to the base 2. Because computer scientists use log base 2 so much, we invented a symbol on our own, just LG for short, to use that. Then there's ln, which you should have seen in some math classes, which is the natural log, log base e. And sometimes you also see an abbreviation for log base 10. Do you know an abbreviation for log base 10? What would you use? Just log? So like this. Log is log 10. Okay. So I will not do this because we never need log 10. So we might as well keep log free. Log without anything, I will make sure. I hope I can keep up to that promise. I will try to make sure that I use log without a base only in a big O term. Because in a big O term, the base doesn't matter. It's only a constant factor, so you might as well drop it. So it's common practice, I'd say, in computer science to write things like this. You specify the base of the log on the left side where it matters, but then inside the log you ignore it and you just write log without any specific base. Okay? Well, the last example is just to say ignoring constants could give you deep trouble. This is certainly one Google, I think, is that. It's a humongous number, ridiculously large, but it's still constant, so it's big O of 1. We hopefully won't have constants like this in our algorithms, but, well, the mathematical definitions don't care about reasonable constants. Okay. Let's do another one for you. A slightly more complicated example. I'll leave the timeout with 1 minute. That's probably not enough time to type the stuff into Wolfram Alpha, so just think about it for now and then type it in later. But computing the limit is not very challenging for this problem anyway, so. Okay, it's roughly an equal split. Well, maybe not quite, but almost. So it's indeed true. It's in big theta. To convince you, or maybe proof in the computer science way, I shouldn't have said that. I have to delete it from the video. To convince you, let's type it into Wolfram Alpha and see what happens. The interesting part here, as you can see, is the limit doesn't exist in this case. I can take the quotient of those two functions, fine. But if I take the limit, it keeps oscillating between 1 and 3. And that's a problem for computing limits, but it's not a problem for computing the Lehm soup that you've seen on the slides. You can take the largest value of all limits. That's one way to solve it. The other way to solve it is whatever it is between 1 and 3, hey, that's still bounded. It's not infinity, so who cares? So it's bounded. That's why it's big O. It's also bounded away from 0, so it's big theta. So that was just to briefly point out, big theta usually means we just ignore constants. Sometimes it means we ignore constants, but there is no single constant that would take its place. This is basically a collection of things that are useful for computing with this. It's just basic things. So if you have a function, you multiply it by a constant, that leaves you in the same theta class because it ignores constants. And if you add two functions up, that's the same as taking the bigger of the two. And that's it's also true in the other direction. You will work more on those in the tutorials. There's a few orders of growth. I will usually use order of growth and theta class synonymously. So if I say logarithmic growth, then it's theta of log n with some constant that we don't specify. And there's a couple of more orders of growth that occur somewhat frequently. And you will talk about some more examples from these classes in the tutorials. So one thing I pointed out before, for logarithms, the base doesn't make a difference as long as it's both constant. For exponential functions, the basis, so the c that's at the basis of the exponentiation does make a difference. So 2 to the n is way smaller than 3 to the n, also in the sense of big O or big theta. The last thing I want to do today is a small example with an actual algorithm. So all the time we talked about only the math part, and I invented some functions that you might agree never occur. So here's a function that actually occurs. It's not super important what this algorithm does. It's a way to take some real number x and compute x to the m, the mth power, but the power, the exponent is an integer. There's many ways to do this. You might as well just multiply x with itself m times. And you can think about whether that's the smartest way to do it. It's not. Here's a way that's a little smarter. To make this concise, m is given as a binary number, so as a list of the bits of digits. That's that part. And we'll call the number of bits n. Now, of course, you can relate those two. We'll come back to that. And x is just some float, a double number in that case. So here, this is actually Java code. You can type it in if you want and play with it. So that computes this exponent. I don't want to discuss really how it does it, because that's irrelevant for what I want to talk about now, but you're invited to check that. So let's try to analyze how costly it is to run this algorithm. And our cost measure will be the number of multiplications, which is basically all this algorithm does, so that seems like a reasonable abstraction. So how many multiplications do we need? We do one here and one here. For the line 4 multiplications, it's easy. We just iterate over all the bits. If I have n bits in total, that will be n multiplications. For the second multiplication, it's a little more complicated because there's this if. It's not always executed. It might sometimes be skipped whenever bit is 0 or false. So the only intelligent thing we can say is this multiplication is executed as often as we have 1 bits in the binary representation of our number m, because that's exactly these exponent bits. Okay? Now I give you some number m. You write it as a binary number. It will have a certain amount of ones. Is that clear, or shall we do an example on that? Or we can do a tiny one. I can do a tiny one. Let's say it's 5. So if I write that in binary, that's 1, 2, 4. So it needed 3 bits, 2 of which are 1. Is that correct or not? Sounds good? So what we can say about C is it's at least n, because this could be at least nothing. So that's the lower bound. And the number of 1 bits in M can at most be all bits. That's another n. So C is between n and 2n. Okay. Now that's all you should take from that slide for now. I want to add though that the number of bits to write M, I get confused with this. The number of bits you need to write n is essentially something like this. So you take your number, sorry, this should be, you take m plus 1 because you have to encode the 0 also, then you take the log base 2, and then you round up because we can't use half bits. So n is essentially logarithmic in m, right? We just learned that this is theta of log n. Well, this would need proof, but maybe we can just believe that, or you type it into Wolfram alpha. We can even say n is tilde log n. That's another statement you can make. Again, type the quotient into Wolfram alpha. It hopefully will spit out the correct answer. So this result is not too bad. To compute this power, the number of multiplications we do is just logarithmic in the size of m. If you went ahead and just multiplied x m times with itself, that would be m and not log m. Okay? So it's a good algorithm, but I want to make another statement about this. And so this is the last question for today, I think. No. There it is. For answering that question, you can essentially ignore everything about this algorithm. Important is just this statement. It was an open-ended question, which is a mean thing to do. Okay, I see reasonable stuff. Can you see everything? There's no clear winner, right? It was nasty of me to ask for the most precise statement, because that's a bit open-ended. But the answer in this case is theta n. I don't know if okay, I put it here. C is bounded between n and 2n. So if I take the quotient c divided by n or c divided by 2n, in both cases that quotient remains bounded away from 0 and away from infinity. That's how you can prove that it's theta n. And again, essentially a second example of the lesson. Theta is like tilde with an unknown constant, except that sometimes there is no constant. It could be a range. And in this case, it's the range 1 to 2. Okay? So this time before you go, I want to try this feature of Pingo, where you just have before you go, a quick feedback on how you liked the session today. The isolated evaluation will not be that interesting, but over time, when I can compare different sessions, I can see which ones worked well and which ones didn't. So I'll try to make this a habit and hope you'll remind me in case I forget.